Okay, so let's begin. So as I was telling that we will start with electrical conductivity of metal. So today we are going to start with electrical conductivity. Now, when we say electrical conductivity, so first there is a term which is called current density. So we are going to explain what is current density. There are a few definitions that we should understand. One of them is current density. Now, what is current density? Current density, first of all, it's a vector. Usually we denote it as J with, of course, arrow sign. This arrow marks on the head makes it a vector. So it signifies that it's a vector quantity. Now, for those who are coming from 10 plus 2 and probably need to brush up their memories, you should remember the quantities. Any physical quantity can be either of two classes. It can be either a scalar or it can be a vector. Now, scalar are the quantities which have only magnitude. For example, let's say mass, time, length. These are the quantities that have only magnitude. But there are few special or there is another class of quantities which comes with two aspects. One is, of course, magnitude, and the second one is direction. So those quantities or observables rather, observable is something that you can measure experimentally. That comes, so those observables that comes with both these two aspects, that is magnitude and direction, they are called vector quantities. And this current density is one. So what is current density? Current density is current flowing per unit area, normal to the direction of flow. So this word we must emphasize. We must mention that that area should be normal to the direction of flow of charge. That means direction of current, let's say. So what is normal? Normal is not perpendicular. So normal, as we know, it actually a surface can be a norm. I mean, normal is like, let's say, a straight line which is perpendicular to the tangent drawn at a point on that surface. So in simple word, let's don't get mess up with tangent, perpendicular and all that. Remember, perpendicular and normal are not same. Although they are very identical looking, they are very similar looking, but they are not exactly same. We cannot use the word perpendicular here. We must use normal. So what is normal? Normal is a straight line which is perpendicular to a tangent of a surface at that point. That means we have a surface, let's say, and let's say this is the point. So at this point we draw a tangent to this surface. Tangent means a straight line that touches this surface only at this point, and then on this tangent, let's say this index finger is the tangent. Now this on this tangent we draw a perpendicular at that point where the tangent is drawn. Now this straight line is now the normal to the surface, to this surface at this point. So when we say the current per unit area, we must mention that the area must be normal to the flow of charge. That we must mention. So this is called current density. Now, current density, what is the unit of current density that we should remember? Now, since this is current per unit area, so the unit of current is ampere, as we know, and then per unit area. So what is unit of area? Well, we know it's very simple. It's meter square. So ampere per meter square, or ampere meter to the power minus 2. This is the unit of current density. So we should remember this definition, that what is current density and what is its unit. And also we should remember that current density is a vector. Although we will try to keep our analysis and everything at a very basic level, making it just only considering the magnitude, we should remember, and that current density is a vector. Now comes there is another quantity which is called number density, which is denoted by small n. So what is number density? So if we look at the this is word, first is a number. So of course, this is a number is number, and then there is something called density. So density, if we consider mass density, then we know from our knowledge of 7th standard, 8th standard, or even 9th standard, that density is mass per unit volume. Mass of a body per unit volume. That means if D is density, then it is mass, that is m, divided by volume, V, volume of that body. So m by V. So number density is number of particles per unit volume. So in simple words, suppose we have a volume of some object, something, let's say it's this room, and we want to calculate how many human particles are there. So what we are going to do, first we need to count the number of particles. That means how many humans, what is the number of human particles present in the room, that we can count, like 10, 20, 30, 60, depending upon the size of the room. And then we need to calculate the volume of the room. So volume of the room is a parallelepiped, or simply like can multiply. How to determine the volume? It's simply the multiplication of length, width, and height of the x, y, and z. So if I know the volume, then the number of human particles divided by the volume will give me number density of human particles in this room. Similarly, it can be like number density of electrons in a metal or something else. Now, what is the unit? Now, since this is the number of particles, so that does not have any unit. It's just a number. Might be 10, 20, 100, 10,000, 1 lakh, 10 to the power 19, 10 to the power 91. I do not know. It's some number divided by volume. So, what is the unit of volume? The unit of volume is meter cube. So, it's number divided by meter cube. So, overall, this becomes meter to the power minus 3. So, please do remember that the unit of number density is meter to the power minus 3, or per meter cube. Per meter cube. This is the unit. Now, the last one that we should remember is called drift velocity. Drift velocity. Drift velocity is an interesting point, and we should remember this. That what is drift velocity? Now, first let's try to understand what is velocity. So, you all know from 10 plus 2, or even classes from 7 standard, 8 standard, velocity is displacement per unit time, which is a vector. But then there is an additional word, and this additional word is drift. So let's remove this and just try to highlight the one so that we can. So this drift word is the new. What is drift? We can understand this velocity, but then from where this drift comes from? So to understand this, let us consider a scenario, a very simple scenario. Let us consider the Howrah Bridge. We know all about Howrah Bridge. It connects between the it's over the river Ganga. So one side we have Howrah railway station, and the other side we have the city of Calcutta. So it basically joins between the city Calcutta and the Howrah railway station. So on this Howrah Bridge, if we see, is on every day on daily basis, cars, buses are moving in both directions. That is from Howrah to Kolkata, or in the other way, that is from Kolkata to Howrah. So to understand this drift concept, let us consider a hypothetical situation that there is only one-way traffic allowed through the Howrah Bridge. That means only buses are coming from the Howrah station to the Kolkata. No other way, only one direction. So all the vehicles, be it car, bus or whatever, they are moving from Howrah station end to Kolkata end. But then, are they moving parallel to each other like a very single file line or like very streamlined motion? The answer is no, absolutely not. They are moving in their own direction. Someone trying to bypass some vehicle, someone trying to overtake. So overall, the traffic is moving from Howrah station end to Kolkata end, but the individual velocity, the individual direction of the velocity of each car, they are not parallel to each other. They can be different. This is exactly what happens in a metal. So suppose we have a metal strip which is under an external electric field. Let's say the electric field is moving from left to right side. So under the influence of the electric field, electrons will move exactly in the opposite direction. This is what we should always remember in this course. Do not forget this. This is something like some tips that we say that you should remember throughout your life. This is one of them. That free electron moves in the opposite direction of the applied electric. The electric field is acting from north to south, then the electrons must move from south to north, exactly in the opposite direction. So exactly in the metal, what happens that under the influence of the electric field, of course, the electrons are moving in the other direction, but they are not moving parallel to each other. They are not well civilized, well disciplined students like the students of Brentwood that everyone is sitting in the class a proper way. They are, when they go out of the class, they leave the classroom one by one. No, not like that. Although this scenario is not very familiar in anywhere, at least in your class maybe, uh, because once the class is over, everyone is trying to get out of this class, particularly at the end of the if it is the last class for that day. So we have a rush to go home, whatever, do our own business. But then, exactly this is also happens inside a metal. So every electron is trying to move from in the opposite direction of the applied electric field, but they are not moving back. And that is where this drift word comes from. So electrons are getting drifted from the positive end of the from towards the positive end of the conductor that we know. But again, they are not. So it's an average velocity because they are not moving parallel to each other. So it's an average velocity of electrons that is electrons getting drifted towards the positive end. What is drifted means as if they are getting pushed. They are getting drifted towards the positive end of the electron of the conductor under the presence or in the presence of the external electric field. If there is no external electric field, then there is no drift velocity. And drift velocity is zero because then electrons are moving completely random direction. So when we make an average of completely random velocities, that comes to zero. But in the presence of electric field, of course, electrons move in a certain direction. That means towards the positive end of the conductor. But that does not mean that everyone is moving parallel to each other. Every one means here the electrons. Each electron is moving parallel to the other one. They're moving in their own way. They are finding their own way. But the overall direction of movement is fixed. That is towards the positive end of the electric field. Or in if I consider or if I compare the example that we started with, then electrons are moving from outer station into the Kolkata. That is true. But again, the Howrah bridge, they are not moving all the electrons, they are not parallel to each other. They are taking their own path. So therefore, the drift velocity is the average velocity with which free electrons gets drifted towards the positive end of the conductor under the influence of an external electric field. So this is called drift velocity. Fine. So now these are the few terms that we should remember. So one is of course number density, the current density, and drift velocity. Good. So now let's see what is next. So now we know current density. So this current density can also be calculated, or there is an expression of current density which is NEVD. NEVD. You see this one. That where n is number density, E is charge of electron, and Vd is the magnitude of velocity. So this is the magnitude. You see, we do not have any arrow mark on top. This is only the magnitude of velocity, which is NeVd. Now you may ask, there is a minus sign. Why you are not talking about the minus sign? So this minus sign is because we are considering electron. So electrons have negative charge. So this value of E, what is the value of E? 1.6 into 10 to the power minus 19 coulomb. 1.6 into 10 to the power minus 19 coulomb. But with a minus sign to indicate that this is an electron which has negative charge. Now, how can we derive this? We will come to it in the next session. At this moment, for this moment, let's only consider the basic idea and then exactly how we can calculate this, how we can arrive at this expression of J equal to minus NeVd. We will come to it later. Let's be patient for, let's say, for the next session. So we now know what is J, what is the expression of current density. Now, using this classical free electron theory, Drude arrived or derived rather an expression of electrical conductivity. Now remember, this expression of this electrical conductivity sigma, which is denoted by sigma, this is a Greek letter S, Greek S, the small s, sigma. This denotes electrical conductivity. Now, electrical conductivity, the expression of electrical conductivity was derived by Paul Drude after rigorous calculation and all, which at this moment we are skipping. This is, we don't want to burden you with all that, the direct derivative and all that. But then of course at this moment we will only consider the expression. The expression of electrical conductivity is sigma equals n is square tau over m. N is square tau over m. So we should remember this expression. So this is sigma. Sigma equals n e square tau over m. Now all the symbols that already we are familiar with. So if I go one by one, then this n is number density. So number density is number of electrons per unit volume. This is n. Then we have E with square. So what is E? E is charge of electron. Then we have tau. Tau is called relaxation time. And m is mass. Mass of what? Of electron, because we are considering only electron. So this is the expression of sigma. Sigma is n is square tau over m. This expression comes from Drude's prescription. Now if you look at it, then this value of E and m, these are constant because charge of electron and mass of electron, they do not vary. Only the value of n and tau varies, and that is why for different metal, since we have different values of sigma electrical conductivity, so only the the symbols that have different values, or rather the variables, are this n and this tau, because E and m remains constant for any. So we know these are, now this is important, and that is, what is the unit of sigma? What is the unit of electrical conductivity? We call it as Siemens per meter. Siemens per meter. But again, so Siemens is symbolized as S, capital S, per meter. But if you cannot remember this, then there is also an easy way. What is that? Now we know electrical conductivity is reciprocal of resistivity or inverse of resistivity, electrical resistivity, which is usually denoted by rho. This is also a Greek alphabet equivalent to P. So this rho, no, sorry, not P, but R. That's a mistake, because equivalent of P would be pi. Now 1 over rho, where this is rho is the resistivity. Now resistivity has the unit of ohm meter. So if the unit of rho is ohm meter, that is the unit of resistivity, then sigma, which is inverse of rho, then it will be sigma ohm inverse meter inverse, or this ohm inverse is actually called Siemens, and that is why the unit of sigma is Siemens per meter. So this we should remember. Now using this classical free electron theory, this is the advantage or success of classical free electron theory, that it can accurately determine the value of electrical conductivity. So if we know the value of tau and n for different metals, we can calculate the value of sigma, and that value will be very similar to what we get when we measure it experimentally. That means the theory can match with the experimental. That is why we say that the classical free electron theory is a success, because it can accurately estimate the value of electrical conductivity. This is its success that we should remember. Now, in this scenario, we should also remember another topic, which is called mobility of electrons, but we will not go to this at this moment. We will continue this in our next session. So from there, in the next class, we will start with the mobility of electron, and then also we will consider the thermal conductivity of metal, and we will see how classical free electron theory can accurately explain the thermal property or thermal conductivity of metal as well. However, we will also see that there are few mistakes as well. Inherent mistakes are there inside, in that expression that we derive for theory, thermal conductivity, but that we for next day. So for today, if we try to understand what we have learned, we learned few basic definitions like current density, then we what is number density, then what is drift velocity, and then we understand, we learned what is the expression of J, that is current density, J equal to minus NEVD. Why there is a minus sign? And then lastly, we learned about the expression of electrical conductivity as derived by fault-fitting. And surprisingly, using some very basic assumptions, some of the too basic, or rather against our general understanding, even then this very simple model can accurately estimate the electrical conductivity of metal, which is its success. So this is what we learned, and we will not go any further. So we will see you in the next class.